Thank you, Gabriel. Thank you, Gabriel, for the invitation. I'm very happy to speak at this seminar. And thank you, everyone, for coming to the presentation. I'm going to speak about standard quotients of homogeneous spaces, case of plane waves. So in this title, we have two things. First, we have standard, what we call standard quotients. And on the other hand, we have what we call plane waves, which are special Lorentzian manifolds. So in the first part of the talk, I will develop the notion and motivate the notion of standard quotients of homogeneous spaces. Then in the second part, I will speak about, I will move to plane waves. Okay. So the general question for this talk is the following. What are the homogeneous spaces on which compact manifolds are modeled? So, okay. So what is a homogeneous space? Homogeneous space is a smooth connected manifold on which I have a transitive action of some Lie group J. So if I have a manifold with a transitive action of a Lie group J, then I can identify X with the quotient of J by some subgroup which fixes some point of X. So X is identified with the right quotient J mod I, where I is a subgroup of J fixing a base point in X. And this group I, we call it the isotropic group. It is a closed subgroup of J. So this is what I mean by a homogeneous space of a Lie group J. And now, if I have a homogeneous space of some Lie group J, then I can define what we call a compact quotient. A compact, which are new manifolds, which we can build from this space X. So a compact quotient of X is a quotient of X under the left action of a subgroup gamma of J, which acts properly, freely, and co-compactly on X. So X is a homogeneous space of J. So it identifies with J mod I. So I have the Lie group J acts on the left by left multiplication on the coset space. And the quotient of X is the quotient of X under the action of a subgroup of J, of a discrete subgroup of J, gamma, which acts properly, freely, and co-compactly. These conditions here, the first two conditions ensure that when I take the quotient M here, I get a manifold. So freely means that it acts without fixed points, and properly it's the condition I wrote here. For any compact subset of X, this set here is compact. Is compact inside J. And if gamma is discrete, in fact, properly means that this set is finite. Okay, co-compactly means that the quotient is compact. So quotients of X are particular cases of manifolds locally modeled on X. So a manifold locally modeled on X is in the language of GX structures. It's a manifold which has the local structure, which is locally isomorphic to X. I'm not going to give the exact definition of what a GX structure is. This is not the point of my talk. But what I can say is that a priori, quotients of X are particular cases of manifolds modeled on X in the sense of GX structures. But when the structure is complete, this is some notion related to GX structures. When the structure is complete, then the manifolds locally modeled on X, locally isomorphic to X, are exactly the are exactly the quotients of X. When I have completeness of the X structure, then a manifold locally modeled on X is exactly a compact quotient of X. So the question I gave in the beginning, I said, given a homogeneous space, the question is the following: is there a compact manifold which is locally isomorphic to X? So this is a more general. So I have on one side I have this question. Given this homogeneous space, I can ask whether there exists a compact quotient. And in general, the first question is more general than the second one. But again, when the structure is complete, the two questions are equivalent. And in my talk, all the structures I will see are complete. So for me, looking for compact manifolds locally isomorphic to the homogeneous space I fixed in the beginning is the same as looking at compact quotients. Okay, so some examples here. We have some examples of homogeneous spaces. We have the affine space on which we have the affine group of Rn which acts transitively on Rn, the usual action. And we have the complete models of Riemannian manifolds of constant curvature. So we have the Euclidean space, the Riemannian sphere, the hyperbolic space, and the Lorentzian analogues. For Lorentzian analogues of constant curvature, we have Minkowski space-time, the de Sitter space, the anti-de Sitter space. All these are homogeneous spaces. The main difference between the Riemannian case and the Lorentzian case. So in the quickly, a Riemannian manifold is a manifold on which I have a Riemannian metric. So a Riemannian metric has index n, where n is the dimension of the manifold. For a Lorentzian manifold, the index of the metric is 1n, where n plus 1 is the dimension of the manifold. So I have vectors of negative norm. And the main difference between the Riemannian models and the Lorentzian models is the fact that the isotropy group here, the isotropy groups in the Riemannian case are compact, and the isotropy groups in the Lorentzian case are non-compact. So now, given homogeneous space, there are three general problems we can study. We can study. The first one is this question of completeness I mentioned in the beginning. This is not the question I'm going to develop, but I will mention quickly what we have here, and then I will give the two questions I will be developing in this talk. So first, this first question, it's an important question which is widely studied, and the question is the following: is any compact manifold which is locally isomorphic to X complete? Is it complete? So first observation is when J preserves before this, just to give an idea of this completeness question. In fact, when the group J preserves a connection on X, if it preserves a connection on X, I can speak about geodesics of X. And if I have geodesics of X, I can speak about geodesic completeness. And the manifold is said to be geodesically complete if the geodesics are defined on R. In the case where J preserves a connection on X, and if X itself is geodesically complete, then this notion of completeness of a manifold locally isomorphic to X is exactly is equivalent to the geodesic completeness of M. And the observation is the following: when J preserves a Riemannian metric on X, then the answer to this question is yes. Then any compact manifold modeled on this geometry is complete. But in the non-Riemannian situation, meaning that when J does not preserve a Riemannian metric on X, the analog statement is not true. So there are situations where the structure is not complete. And one of maybe the most famous result of completeness in the non-Riemannian situation is a completeness result due to Carrière in the Lorentzian setting. So it says that any compact flat Lorentzian manifold is complete. So geodesically complete. As I said in the beginning, when I have this completeness condition, then any manifold, then any compact flat Lorentzian manifold is identified with a compact quotient of the flat Lorentzian model. And the flat Lorentzian model is the Minkowski space. So in this case, any compact flat Lorentzian manifold is identified with the quotient of Minkowski space by a discrete subgroup gamma of the isometry group. And the isometry group is the extension of the abelian group of translations by this linear group, which is the orthogonal group preserving the Lorentzian scalar product on Rn plus 1. Okay, so with gamma, of course, acting properly, freely, and co-compactly. So the other two questions in this setting are the two questions I wrote here. So first, existence of compact quotients, and then Bieberbach rigidity. Bieberbach rigidity, I'm going to explain what this is. We call this Bieberbach rigidity or standardness question. I'm going to say what this is. But so about the question of existence of compact quotients, we know that there are geometries. We have homogeneous spaces for which there is no compact manifold modeled on it. And one of the oldest results in this setting is what we call in this question is what we call Calabi-Markus phenomena. So the result is the following: the only discrete subgroups of SO1n acting properly on de Sitter space. So the de Sitter space is the Lorentzian model for constant curvature plus 1. So it's a complete Lorentzian manifold of curvature plus 1, a positive curvature. It is a homogeneous space. And the isometry group, the connected component of the isometry group is exactly SO1n. So I have a transitive action of SO1n on the Sitter space, and this space identifies with this homogeneous space. And this result says that the only discrete subgroups of SO1n acting properly on the Sitter space are finite. So as a consequence of this, there is no compact quotient of the Sitter space because all discrete gamma acting properly are finite. So there is no compact quotient of the Sitter space, and in fact, there is no compact manifold locally modeled on the Sitter space. So there is no compact Lorentzian manifold with the constant curvature plus 1, or with the positive constant curvature. So regarding this question of existence of compact quotients, there is a difference between the case where the isotropy group I here is compact, or and the case where it is non-compact. In the compact case, this is so when the isotropy I is compact, this corresponds exactly to the case where the group J preserves a Riemannian metric on X. So the space X becomes a Riemannian manifold. In this case, the the action of J on X is proper. So the action of the whole group J, the whole group J acts properly on X. So any discrete subgroup of J also acts properly on X. So here, asking that my discrete group gamma of J acts properly, the proper condition here is automatically satisfied just by the fact that gamma is a discrete subgroup. Okay, so here the discrete subgroups of J acting co-compactly are exactly the co-compact lattices of J. So here the question whether there are compact quotients translates into the question of existence of co-compact lattices of J. And this Riemannian situation is extensively studied and well understood. In the non-compact case, when the isotropy is non-compact, in this case, J, the group J, does not act properly. Because one necessary condition to have a proper action is to have a compact isotropy group. Here, it's not when the isotropy is not compact, the group J does not act properly. So here, if I take a discrete subgroup of J, the properness of the action of gamma is a true condition here. The fact that gamma is discrete does not imply that the action is proper. So in this setting, when the isotropy is non-compact, the properness condition here is a true condition. And in fact, this is the main source of difficulty for this question. The difficulty is to find discrete groups acting properly. It's this proper action in general is difficult to check. Okay, so the first situation contains the Riemannian spaces. In the second situation, we can find many geometric structures. So the affine structures, conformal structures, and Lorentzian structures. And in fact, the geometries or the structures I'm interested in are the Lorentzian structures. So, and they belong to this second situation. So now I'm going to give examples of discrete subgroups with non-proper actions. I said that discrete, when the isotropy is non-compact, discrete does not imply proper. I'm going to give an example. So,
excuse me, Lilia.
Yes?
One question.
Uh-huh.
You explain a result about positive curvature.
Yes.
Is not something in the case of the negative curvature? To model Lorentzian manifolds with. Are there compact Lorentzian manifolds with negative curvature?
In odd dimension, yes. In odd dimension, there are compact quotients. So for Lorentzian manifolds of negative curvature, in odd dimension, we have existence of compact quotients. And in fact, there is an idea construction introduced by Kulkarni, which constructs explicitly the compact quotient given the model space, but not in even dimension. There is no compact quotient.
Interesting. Thank you.
Okay, so here this example will be Lorentzian manifold of negative curvature, constant negative curvature in dimension 3. So this is the zeta space of dimension 3. I will give non-discrete subgroups of the isometry group with non-proper action. So first, I will recall a model of this space. A model for the zeta space is given by a left invariant metric on the group PSL to R. So we consider how to construct the antidesita space of dimension 3. The construction goes as follows. So consider the Lie group SL to R, which are 2 by 2 matrices with determinant 1. The Lie algebra of this group is made of a matrix 2 by 2 matrices with trace 0. So you can think of the Lie algebra of a Lie group as the tangent space of the Lie group at the identity. So consider a matrix in the Lie algebra of SL to R. So you can think of A as a vector on the tangent space of the Lie group at the identity. This quadratic form given by minus the determinant of A. So minus the determinant of A is A squared minus BC. This quadratic form on this space has a Lorentzian signature. Okay, so I take this quadratic form on the Lie algebra, so on the tangent space at the identity, and I push forward remember my group is SL to R, and SL to R acts on itself by left multiplication. It acts transitively on SL to R by left multiplication. So I take this quadratic form on the tangent space at the identity, and I push forward this quadratic form at every point of the group using the left multiplications of SL to R. So this way I define a Lorentzian metric on the group on PSL to R. I define a Lorentzian metric such that by definition the left multiplications by PSL to R are isometries. So we call this metric left invariant. Left invariant meaning that the left multiplications of the group on itself acts isometrically on the metric. So I get a Lie group PSL to R with a left invariant Lorentzian metric on it, and this is my space. And in fact, this space is a complete Lorentzian manifold with constant sectional curvature -1, and this is exactly what we call this is exactly the antidesita space of dimension 3. So the antidesita space of dimension 3 is given by a left invariant metric on the Lie group PSL to R. This is my space here is a Lie group. And in fact, this metric J is also right invariant. It's also invariant by right multiplications of PSL to R. So the isometry group is in fact a product of PSL to R with itself, and acting this way. So J acts on the left, and H, the other component, acts on the right. So the isometry group is bigger. So this metric is left invariant. So I already have the left action of PSL to R, which is isometric. But the isometry group is bigger than that. It contains a copy of PSL to R, which acts on the right. So the isometry group is a product. And the isotropy, to find the isotropy, I apply this to the identity X. I take X here to be the identity element in PSL to R. And I find if the identity element is fixed, then H is equal to J. So the diagonal, so the isotropy is the diagonal, which is isomorphic to PSL to R. So it is non-compact. So this is antidesita space with its isometry group. And now I consider the following two examples. The first example, both are discrete subgroups of the isometry group. The first example is generated by two elements in the isometry group, X, which is defined by, in the first component, I take this matrix in PSL to R. This is a hyperbolic matrix, and the identity for the other component. So the element E here is the identity of PSL to R. And the other element Y is this one. I take a matrix B in the second hyperbolic matrix in the second component, and the identity element in the first component. So this gamma, this group gamma is not contained in any copy of PSL to R. It's transversal to both copies of PSL to R in the isometry group. And this is a discrete subgroup, of course, and I claim that it has non-proper action. To see that it has non-proper action, I apply these elements x and y, so all the powers of x and y to the identity. I get this matrix here. And the fact is that this matrix, for many choices, for infinitely many choices of m and n of the powers here, this element is close to the identity. So this means that I have a non-discrete orbit. The orbit of the identity element is non-discrete, and this contradicts the properness condition. So I wrote it here above. The proper action of discrete group implies two things. Implies that I have discrete isotropic group and I have discrete orbits. In the second example, I have this element. So I have a unipotent matrix here in the first component and identity here, and I switch the components. When I apply this to the identity, remember that how do I apply the elements? It's this acts on x by gx h minus 1. So when I apply this to the identity, it's this matrix times the inverse of this one, so it's the identity. And in fact, this group is in the isotropy group of E, and it is infinite. It's gamma is an infinite group. So I have infinite isotropy group. This also contradicts the properness condition. So here I have discrete, these are examples of discrete groups acting non-properly. And both of these groups are isomorphic to Z2 because these two elements here commute. And more generally, Kulkarni and Raymond, they studied discrete subgroups of isometry group of anti-de Sitter space of dimension 3 acting properly. And they proved that the discrete subgroup contained in a copy of Z2 has non-proper action. So these are particular examples. So a general question here is to characterize the discrete subgroups of the isometry group acting properly. How to get such an example? Remember that the isometry group is a product of PSL to R with PSL to R. If I take a lattice gamma in the first component, so I take a lattice gamma of the first PSL to R component, then this gamma acts properly, co-compactly on anti-de Sitter space, because well, the left action of PSL to R on itself is proper. So any discrete subgroup, in fact, inside PSL to R acts properly on itself. So and remember that anti-de Sitter space is exactly identifies with this group PSL to R with its left invariant metric. So any lattice here gives when I take the quotient, I have a compact Lorentzian manifold of constant curvature minus 1. Now I can deform this gamma inside the isometry group. So consider gamma co-compact lattice in this PSL to R, the first component of the isometry group. We can deform gamma inside the isometry group by considering a representation rho of gamma inside this group and defining gamma rho this way. So now given gamma and fixing some representation of gamma in PSL to R, I can define this group. Of course, the subgroup of the isometry group is discrete because the first component here is discrete. And it acts this way. And for the trivial representation for rho equals 0, it's exactly gamma rho is exactly gamma. So if I deform gamma this way, we can ask for which representations rho this new group acts properly. Before that, Kulkarni and Raymond prove that any torsion-free subgroup of the isometry group of De Sitter space acting properly on De Sitter space is of this form I gave before. There is a representation such that gamma is of this form. So the question now is, for which representations is this action proper? For instance, when rho is the identity, gamma rho does not act properly. Because here, the isotropy, sorry. The isotropy groups will, there will be isotropy groups which are infinite. So there are people who were interested with this question. I gave some names here. And in general, characterizing proper discrete actions is a difficult question. So to get at least some examples of compact quotients, Kulkarni gave some idea, some principle to have examples, and the observation is, in fact, this principle led to the notion of what we call standard compact quotients. I'm going to define. I'm going to give the. So what is this idea of Kulkarni? Consider a homogeneous space X of a Lie group J. The observation is the following. If I have a connected Lie subgroup L of J, which acts properly co-compactly on X, then any co-compact lattice in L will also act properly co-compactly on X. So instead of looking at discrete groups acting properly, I will look at connected Lie groups acting properly. If I have a connected Lie group L inside J which acts properly, then any discrete subgroup which will also act properly. And the fact is that looking for connected Lie groups is an easier question. Looking for connected Lie groups acting properly is an easier question than looking at discrete groups acting properly. So you can think of this example of De Sitter space in dimension 3. The isometry group with this product, and here L can be taken to be just one of the components, one of the PSL to R components. This L, the left action on an De Sitter space, or the right action, is proper. So any lattice gamma inside L will also act properly. This was the construction I gave before. So when such a group L exists, if I can find a connected Lie group acting properly co-compactly on X, then the existence of compact quotients becomes an existence question for co-compact lattices in Lie groups. So this brings me to a question similar to that in the Riemannian setting. I'm going to give now. Okay, so I fix the definition here. If I have a homogeneous space of a Lie group J, a compact quotient is said to be standard if gamma is a co-compact lattice in some connected Lie group L of J, which acts properly co-compactly on X. So if I have a Lie group L which acts properly co-compactly, then any gamma inside L will define me what we call a standard quotient. And I wrote here virtually, meaning that in fact I do not require that this is true for gamma, but for some finite index subgroup of gamma. So a compact quotient is called standard if there is a finite index subgroup of gamma, which is a lattice in a connected Lie group L of J acting properly co-compactly. This condition of a finite index subgroup of gamma on the compact quotient, it translates to saying that up to taken a finite cover. So this group L, when I have a standard compact quotient, this group L is called the synthetic whole of gamma inside J. So the standardness question is asking whether a co-compact lattice of J, is asking whether a discrete subgroup of J acting properly freely, co-compactly, is a co-compact lattice in some Lie group J, in some Lie group L of J. I'm going to give some standardness results. So when the Lie group J is semi-simple, I have this example with antidesita space where this Lie group L, the connected Lie group L here, I take it to be just one of the components of the isometry group. Here, Goldman proves that there is a deformation of gamma with this representation rho I gave before. There is a representation for which gamma rho is non-standard. In a few moments, I'm going to give an example of a non-standard situation. So one of the most famous standardness result is Bieberbach theorem, and that's why we also call this standardness property to be. We also call it Bieberbach rigidity, in reference with this result of Bieberbach. So here, consider a compact flat Riemannian manifold. Any compact flat Riemannian manifold is a quotient of Rn by a discrete subgroup of the isometry group of Rn, which is this group here. What Bieberbach proves is that any discrete subgroup of the isometry group, which is co-compact, if I take the intersection with the translation part, with Rn here, then this is a finite index subgroup in gamma. So what does this mean? When I take the intersection of gamma with so for any discrete subgroup of the isometry group, which is co-compact, if I take the intersection with the translation part here, I get a finite index subgroup of gamma. So this gamma intersection with Rn is contained in Rn, so I can take Rn to be the synthetic whole of a finite index subgroup of gamma. So this theorem here says exactly that any compact flat Riemannian manifold is standard, and the synthetic whole I can take as a synthetic whole here is precisely Rn, the translation part. Okay, and this is generalized to the Lorentzian flat case, but this case is much more complicated. So by remember that by Carrière theorem, any compact flat Lorentzian manifold is a quotient of Minkowski spacetime by a discrete subgroup gamma of the isometry group acting properly, freely, and co-compactly. And Goldman, Fried, and Kamishima prove the standardness of all these quotients. In fact, they prove that up to finite index, gamma is a co-compact lattice in a connected Lie subgroup of the isometry group, which acts simply transitively, so more than co-compactly. And they prove that this synthetic whole L is in fact solvable. Okay. How much time I have? 20 minutes. Maybe I'm going to skip this. I'm going to give now the non-standard example. In fact, this example is fits into the examples I study. So this example is a plane wave. I consider an extension of the Heisenberg group of dimension 5 by R. So the Lie algebra of the Heisenberg group of dimension 5 is generated by x1, x2, y1, y2, z, with only non-vanishing, the only non-vanishing brackets are these ones, two non-null brackets. And A plus is a subspace there, isn't this abelian subspace here? I call it A plus. So, so I define this extension of the Heisenberg group as follows. I suppose that R acts on Heis 5 trivially on the center. So the center of Heisenberg group is generated by Z. So this R acts trivially on the center, and it acts by rotation on the planes which are tangent to this one and this, on these two planes. It acts by the same rotation, let's say. Now I consider the Lie group N inside the Heisenberg group with the Lie algebra, this one, which contains the center. Okay, so this is a copy of the Heisenberg group of dimension 3 inside the Heisenberg group of dimension 4, dimension 5. And with a small computation, we can check that this group N is not preserved by the R action. When I apply R to N, it does not map N to itself. N is mapped transversely to itself. Now I consider delta a lattice in N, and I define gamma this way. So the first component here is 2 pi is the period of the rotation. 2 pi is an element in R. 0 is is the component within the Heis 5, the Heisenberg group of dimension 5. So gamma is the product of the group generated by this element with delta. Now gamma is a discrete subgroup of J. It acts properly co-compactly on X. And the claim here is that gamma is non-standard. And the non-standardness of gamma follows precisely from this fact. Because if gamma is standard, then gamma is a lattice in some Lie subgroup L of J. And this Lie subgroup L of J, because it acts co-compactly, it will have a non-trivial projection to the R component. And if I take the intersection of L with the Heisenberg group, it will be exactly N. The intersection of this group L with the Heisenberg group is N. This means that there is a one-parameter subgroup of J with non-trivial projection to R, which preserves this subgroup N. And this fact says it says that for alpha different than plus and minus 1, N is not preserved. So gamma is not standard. And in fact, I have this homogeneous space admits a non-flat J invariant Lorentzian metric, and this metric is a plane wave. So now I'm going to introduce plane waves. Morally,
May I ask a question? And do you have any information about the curvature in this non-flatness result that you have?
in fact, plane waves. I'm going to say this. The plane waves are flat along some codimension 1 foliation, and transversely it can be. I don't know in general, but it can be a priori. It can be anything. But I know that there is codimension 1 subspace on which the curvature is flat. And so this is what I was going to say. In fact, the plane waves can be thought of as deformations of Minkowski spacetime. So they are not flat. I do not have a flat, an affine flat structure on them. They are not globally flat, but we keep the flatness condition along a codimension 1 light-like foliation. So the general context for plane waves is the one of what we call Brinkmann spacetimes. What is a Brinkmann spacetime? So a Brinkmann spacetime is a Lorentzian manifold which admits a parallel null vector field. So parallel with respect to the Levi-Civita connection of J. Null means that its norm, J norm, JV is 0. So if I have a Brinkmann manifold, then with V, the parallel null vector field, then V is a Killing field. It generates a 1-parameter group of isometries. So by definition, V is parallel. So the orthogonal distribution also is parallel. And since it is parallel, it is integrable. So it defines a foliation. So I have a codimension 1 foliation, which is tangent to the orthogonal to this distribution. And the restriction of the metric on it is light-like. So I have a light-like codimension 1 foliation, which is totally geodesic because the distribution is parallel. So I have an induced connection. If x and y are tangent to f, then nabla xy is also tangent to f. So I have an induced connection on each leaf of this foliation. And a special class of Brinkmann spacetimes is known as PP waves. A PP wave is a Brinkmann manifold for which the leaves of this foliation with respect to this connection are flat. So a PP wave is a Brinkmann manifold plus this flatness of the leaves. And a plane wave is a special case of PP wave. It is defined as a PP wave with this extra condition on the Riemann tensor. This is also equivalent to having local coordinates in which the metric takes this form here. Remark that when S equals 0, I get exactly the flat metric. There is another characterization of plane waves using the isometry algebra. So I'm going to because this is the general definition of plane waves. I want to study homogeneous plane waves. So I suppose that I have a transitive action of the isometry group. So the first task is, given homogeneous plane waves, is to find the isometry group. What is the structure of the isometry group? So I'm going, and I start by defining some objects I will need. So first, the Heisenberg group of dimension 2n+1. So it's defined to be a subgroup of the affine group of Rn plus 1, defined this way. So it's Rn semi-direct Rn plus 1. Rn plus 1 here is, these are just the translations of Rn plus 1. Okay, and this part here is a subgroup of the linear group. So these are matrices which are unipotent, and alpha here, it can be any element in Rn. So the Heisenberg group of dimension 2n plus 1, it can be seen as an affine group. It is this subgroup of Rn plus 1. So here, the center of the Heisenberg group is one-dimensional. It's exactly the eigenvector of the one eigenvector here. The vector 1, 0, 0, 0 in Rn plus 1. It's fixed by all these matrices, so it commutes with everything. And it is exactly the center of the Heisenberg group. The linear group here is abelian. I call it A+. And the remaining translations, when I remove the center, I have an abelian group of translations, which I call A minus. Now I define what I call the affine unimodular light-like group. This is an extension of the Heisenberg group of dimension 2n plus 1. So I consider the vector space Rn plus 1 with coordinates v, x1, xn, endowed with this quadratic form here. This is a degenerate quadratic form, and its kernel is one-dimensional. Its kernel is generated by v. The group of affine isometries of this quadratic form, which preserves v and preserves, the group of affine isometries which preserves this isotropic vector v and which preserves this quadratic form q, is exactly this group, which I call, which I denote by Lu, and which is given this by this group. So here Rn plus 1 is the group of translations. When Rn plus 1 acts on Rn plus 1 by translations, it preserves the vector, the vector v. It preserves this quadratic form, and these are affine transformations. Now these matrices also preserve the vector v because of the eigenvalue 1 here. Here A, I have an element in the orthogonal group of dimension n. So this A, matrix A, preserves this quadratic form, okay? And in fact, if I add any element alpha in Rn, this matrix also preserves everything. So when the matrix A here is the identity, what I get is this group I gave here. I get exactly the Heisenberg group. So if I add any element in On, I get an extension of the Heisenberg group by the orthogonal group. And this is exactly the automorphism group of this structure. What's the structure here is, so it's Rn plus 1 equipped with the flat connection. This degenerate quadratic form and this vector. The automorphism group of Rn plus 1 preserving all this structure is this group. And I call it the affine unimodular light-like group. And now if I have, now if I have a PP wave, so let x v be a PP wave with v the parallel null vector field. If I look at the local isometries which preserve this, remember that, so if I have v, then I have this foliation which I denoted by f, which is tangent to the orthogonal of v. Now if I consider the subalgebra of the local isometries which preserve some leaf and preserves this vector v, in fact, because the leaves of a PP wave are flat, so these isometries preserve the flat connection, preserve the induced Riemannian flat metric, and preserve the isotropic vector. So this is exactly the automorphism group of this structure. So this local isometry is local isometry which lives inside this group, this affine unimodular light-like group. So I have a representation of this inside the Lie algebra of this group. Lie algebra instead of the group because I only have local isometries a priori. So for whenever I have a PP wave, the subalgebra of the isometry algebra fixing some leaf and fixing and preserving the vector v admits a representation here. And the plane wave is a PP wave for which the image of this representation contains the Heisenberg component, the full Heisenberg group. So I can take this too to be a definition of a plane wave. And in fact, this is mainly due to a work of Blow and Laughlin. They have a very important paper on homogeneous plane waves. And they show that for indecomposable plane waves, the isometry algebra contains the Heisenberg, this Heisenberg algebra dimension 2n+1. But in fact, it's true for without this condition of decomposability. So it's true, in fact, for any plane wave. So now, to study homogeneous plane waves, so this is a joint work with Malik Anunay, Nascat, and Zegib. What we do first is to describe the isometry group, and the isometry group is I said before that the isometry algebra contains the Heisenberg algebra dimension 2n+1, and this is what we find here inside the isometry group. We find the Heisenberg group of dimension 2n+1, but we have more. We have some subgroup of the orthogonal group, and an extra one-dimensional, an extra one-parameter group. So the isometry group of homogeneous of a simply connected homogeneous plane wave here. So a simply connected homogeneous plane wave, not any space, of course. So this is the isometry group. This is the isotropy. We ask the question we study is the standardness of compact quotients. So if I have XV, a simply connected homogeneous plane wave, then the isometry group is this one. This called dimension 1 foliation. It's given by the left action of the group here, K semi-direct Heisenberg dimension 2n+1. And in fact, this group, if you look at this group, you recognize a subgroup of the light-like unimodular group. This is a subgroup of ON semi-direct Heisenberg 2n+1. And the action of V, this parallel null vector field, is given by the action of the center of Heisenberg. So the result is the following. The homogeneous plane wave is either standard or semi-standard. So inside this semi-standard examples, we have non-standard examples. I gave you an example before, and we understand in general how non-standardness occurs. So the statement is precisely the following. When the projection, so P here is a projection from J to R to the first component. If the projection is dense, which on the manifold amounts to saying that all the leaves of F are dense, in this case, any compact quotient of X is standard. And we have more. We have that the synthetic whole acts and the synthetic rule acts fairly transitively. If the projection is a discrete subgroup of R, this amounts to saying that the leaves are closed. In this case, gamma is isomorphic to a group like this, and in this case we have no standard examples. And the example I gave before in the beginning of the talk is precisely an example in this situation. Before this work on plane waves, there was a classification of compact quotients in the symmetric case. Symmetric case, which we also call Cahen-Ballard spaces, and this was done by Kat and Olbrich. In this setting, the R action here is semi-simple. The R action on Heisenberg group is semi-simple. But for general plane waves, the R action can be anything. Can be unipotent, semi-simple, or a mix of the two. Now to a brief idea of the proof. The main tool we use for the proof is what we call Zeissenhaus lemma. So given a Lie group J, there is a neighborhood of U of the identity such that any discrete subgroup gamma generated by elements inside this open neighborhood of the identity is nilpotent. And it's even stronger than that. We call this strongly Zeissenhaus. If gamma is, so there is a neighborhood U of the identity such that if gamma, a discrete subgroup gamma, is generated by elements inside this open neighborhood, then gamma admits a synthetic rule. Then gamma is a co-compact lattice in a connected Lie subgroup, which is nilpotent. So this says that if gamma is generated by small elements, by elements in some small neighborhood of the identity, then I have what we call a filling of gamma. I have a synthetic rule of gamma. Some comments: when J is Rn, simply Rn, the group Rn, and if I take some discrete group of Rn, what can I take for n here? I can take simply the vector space generated by gamma. This will be a synthetic rule of gamma. And this construction is generalized for the case where J is simply connected nilpotent group. We call this Maltsev closure. But this is not true for when J is solvable. When J is solvable, I don't have the equivalent, something similar to this. I mean this Maltsev closure. I don't have this anymore in a group which is solvable. And in fact, the isometry group of homogeneous plane wave is a mix of a semi-simple part given by K here and a solvable part given by R semi-direct Heisenberg dimension to n+1. And quickly, I'm not going. I will not give the whole proof of this. Just the first case when the projection to R is dense. So I denote by P the projection to R, and by R the projection to R times K. The question is whether gamma can be generated by small elements. So any element in gamma can be written as RKH, where R is in R, K is in K, and H is in the Heisenberg component. First, I will care about the RK component. Can I find generators of gamma with small RK component? So to capture this RK component, I will project into the R times K. If I project, I define R of gamma. The elements there which can be generated by small elements is precisely the elements which have which are projected to the connected component of the identity of this closed group. So I take the projection of gamma, R of gamma. I take the closure. This is a Lie group inside R times K, but this is not connected Lie group. And the elements which can be generated by small elements are the elements which are projected to the connected component contained in the identity. So this is what I denote by R0. So the projection of gamma intersected with the connected component of the identity. If I take the pre-image of this by R, then the elements, and I call this group, what is this sign? Gamma. Okay, I call this group, this is not gamma, I don't remember this sign. Okay, this group can be generated with elements with small RK component. And now the fact that the projection into R is dense, this is exactly how I can translate this. This says that this group here has finitely many connected components. And because it has finitely many connected components, this new group, this subgroup of gamma I defined here, it has finite index in gamma. So I found a finite index subgroup of gamma in which I can find generators with small RK component. So now I'm left with the H component. For the H component, I use this fact here. I use the fact that the Heisenberg group has a one parameter group of homothéties. Just like think of Rn. In Rn, I have homothéties which transform big sets to small sets contained in the identity. This is in Heisenberg group. I also have automorphisms which act as homothéties, which transform big elements into small elements. So I apply a suitable homothéty of the Heisenberg to transform these H elements into small elements. This way I can find small generators of gamma, and this proves standardness. In the case where the projection to R is dense. I think I run over time, so I'm going to stop here. Thank you for your time. Thank you for listening. And if you have questions, please.
Thank you very much for your presentation. Very interesting talk. So let's thank Lilia for the presentation. And are there some questions? I have a curiosity. One slide before you mentioned about Zariski closure. Can you say something about
Where?
the Zariski? What is the Zariski closure?
What is?
Zariski closure of gamma zero. In this slide.
In fact, there is a definition of what is called Zariski closure. In algebraic geometry, we have a Zariski topology.
The zeros of the polynomials.
Yes, the closed
set.
sets are the zeros of polynomials. And but here for the Heisenberg group, in fact, it's only here. It's even simpler. It's if I have a discrete subgroup of the Heisenberg group, it's just the vector space generated by gamma zero inside the Heisenberg group. It's like in Rn. In Rn, if you have a discrete subgroup gamma in Rn, its Zariski closure inside Rn is just the linear space generated by gamma.
Okay. Thank you. Some other question? I have another curiosity. Do you have some idea how long the history of this topic in GX structure is is very long, maybe because I
GX
remember
structures?
this remember me to Felix Klein.
To which claim?
Felix Klein talk about this kind of geometry.
Ah, Klein.
Klein, Felix Klein. But do you have some idea how when this kind of study starts, the GX structures?
Maybe the big for GX manifolds, I would say, well, who was maybe Klein before GX structures, the Klein geometries. I'm not sure who first studied these notions, but this notion of a GX structure as it exists now, I mean the modern definition, is due to essentially to Thurston. So you can find, there is a book, a very nice book of Thurston about GX structures. So they give this modern definition of GX structures, and the most important, maybe the starting theorem in GX structures, which gives the developing map. So if you have a GX structure on a manifold is X it has a GX structure if you have charts with values in X, such that the transition maps are restrictions of elements of J, and the most important fundamental result here is the existence of a developing map. Developing map means that you have says that you have a local diffeomorphism from the universal cover of the manifold of your manifold to X. So this development, the modern definition, you can find that this was, I would say that this was studied by Thurston, Goldman, but a priori, before they extracted this modern definition of GX structures, there are probably what you said, Klein, that defined maybe gave maybe first definitions, but okay.
Okay, thank you. There is a comment in the chat. Fernando Valdez, thank you for the talk. Was very interesting.
Thank you.
So some other comments, Daniel, maybe.
Yeah, I have a question. Thank you for your talk. I think in one of your results, you have the assumption of the space to be simply connected. But I didn't see this assumption anywhere else. Could you say more about why the simply connected part plays a role in
okay.
the proof?
Okay. In fact, sorry. Yes, we took simply connected plane wave. Why? So the thing is that when I have homogeneous, if I consider a plane wave, I said that locally I have local isometries. I always have, if you remember here, I said that I always have local isometries which act which are inside the Heisenberg, which form the Heisenberg algebra. The thing is that in general, a local isometry does not give me a global isometry. Does not extend. Think of an open subset of Rn. The translations are local isometries, but they do not extend if I take a proper subgroup of a proper open subset of Rn. Also take on R2, okay, the Euclidean space. In the Euclidean space, I have rotations which act isometrically and have translations. But if I take a quotient of the Euclidean space by a lattice, by two translations, I have a torus. On the torus, the only elements that act are the translations. So the rotations do not act on the torus, but they act locally. So they act locally, but they do not define global isometries on the torus. So in order to have global isometries, I have to move to the universal cover.
The universal.
They act on R2. They act locally on the torus, but they act globally on the universal cover. And in fact, there is a theorem, there is a result by Nomizu, and it says that any local isometry of a simply connected, what is this? If you have a complete pseudo-Riemannian space, well, the statement is the Riemannian case, but it's general. It's true in general. So if you have a pseudo-Riemannian space which is simply connected and complete, so there is this topological condition of simply connected, and there is geometric condition of completeness. If we have both, then any local isometry can be extended to a global.
Can extend to a global isometry. I see.
So this
Going
is
to
what
the universal cover. I see. Okay. Okay, so yes, you're using local properties, but then you go to the universal cover to get the
exactly
global.
to have the full isometry group.
I see. Oh, thank you.
Okay. So